Battery and charger problem solving. In this video, we'll be covering e-bike battery and charger problem solving, their symptoms, causes, fixes, and flowcharts. Why it matters, because it helps you diagnose and fix e-bike batteries and chargers more efficiently. Prerequisite VODs. This video assumes quite a lot of prior knowledge, so if you need to go back and brush up on any of these videos, feel free to do so. Let's go through a list of symptoms. Starting with the battery is not charging, and then the battery is not powering on the e-bike, but it is still charging. The e-bike fully turns off when riding, or halfway through the ride. The battery is working, but it has reduced range. The battery is not working after an accident, or there is a battery-related fault code in the system, diagnostics, and/or BMS. The causes, starting with the charger, it could be that the charger is a dead unit, or there could be a fuse, wire, or connector issue with the charger. Whereas the battery, it could be turned off or in a standby state. It could have cell issues, meaning that they are either dead, worn, or disconnected. There could be fuse, wire, or connector issues, a BMS protection trigger, a faulty BMS, or impact or water ingress into the battery, or it could be an incompatible system, as in that generation of battery might not work with that generation of motor and controller. Think of like some OEMs such as Bosch or Specialized across different generations. There might be some incompatibilities there. Fixes. Now, we'll go through these fixes in detail, but I'm just starting with listing them so you can see. The charger side, you can look at fully replacing it or cut, replace and insulate a wire, fuse or connector. The battery, you can start by turning on or waking the BMS or checking it for fault codes if it has that capability. You might be able to also update the BMS software if it's applicable. See the OEM of that BMS, replace any blown fuses, clean or replace cables and wires and connectors, replace the BMS itself, replace all cells or a single cell group, which we call a repack, or replace the entire battery. Starting with a video going over what I do for charger testing. If the charger cables are intact, we begin by plugging in the charger and then turning it on. If everything's normal, when the chargers are powered on, the LEDs should appear green. However, if it is plugged in and the LED is not shining any color at all, that means it could be a dud unit, like the one on the top right that I've unplugged to simulate this. The vast majority of chargers will simply just have a red and green LED. However, there are some more advanced ones which have different functions. You want to check on the charger itself to see what the different lights mean. For instance, the Surround charger can flash green, yellow, and red, and even in different cadences, depending on what's going on with the charger and the battery. Going back to our regular e-bike chargers, now we're going to perform a voltage test. This is the 36 volt charger on the right, and I've just got its connector here. I am using the multimeter. I'm going to plug the positive probe inside to the positive connection of the connector, and then I'm going to put the negative probe on the side of the connector on the negative connection, and that's bang on at 42 volts. So that is a good charger. Now, some chargers are a little bit more complicated. When powered on, they can be in a idle or a sensing mode, waiting to be connected into a battery. The idle or a sensing mode might only show a fluctuating voltage between 1 and 5 volts on a multimeter, but when plugged into a battery, this will jump up to the normal usual voltage. This is a good efficiency measure and a good safety feature, but it is only on some chargers you'll find this behavior. Other chargers, for example Bosch, has a function where the charger will not output the appropriate voltage until a 5 volt signal is applied to the third pin of the charger's connector. So therefore they may be difficult to troubleshoot with a standard multimeter, but you may not even need to test these chargers with multimeters, because these advanced chargers usually come equipped with CAN bus or other communication protocols and are smart enough to provide diagnostics to the rest of the system if there is an issue with the charger. In this next example, we're going to touch on charger connectors. Sometimes they can be a slight mismatch in fit, or they can wear out due to many repeated cycles, as in you're plugging it in and removing it many times. Normal behavior on many e-bike chargers is when the charge circuit is closed or it begins, the light on the charger will turn red. However, I want to draw your attention to this example where I'm moving the connector inside the charge port and the light on the charger is actually flickering between red and green because the circuit is breaking due to the loose connection. and will only charge if it's left in a certain position or orientation, unless one or both ends of the connector are replaced. Now back to the batteries, looking at BMS fault codes. So here's two examples. On the left we have a smart BMS which runs through an app, and it has triggered a cell under voltage protection fault code here. To get more details about specific fault codes, feel free to look at the OEM datasheet on the BMS, and on a Bosch system we have error 61 from memory. I think that's to do with just cell under voltage, either on a pack or a single cell group level. Information like this can usually be found on a display or the BMS app like this, or diagnostic software. To find the meaning of each fault, you can plug it into an AI prompt with the brand and the code of the BMS or the system, or search through an OEM manual, because all of them are going to be slightly different. Waking up a BMS. On some e-bike batteries, to conserve power, the BMS may go into a deep sleep mode if the battery has not been used for a long time, and sometimes the BMS will have to manually be powered back on for the battery to work again. So the simple way to do this is, sometimes if they are switch enabled, pressing in a switch, even though some of them are just for battery state of charge testing, it can also trigger the BMS to wake. The other more common and more reliable way to wake a BMS is to plug it into a charger, even just briefly for a second. If it starts accepting charge, it will usually wake up the BMS. Otherwise, you may be able to wake up the BMS by applying load to the battery, or turning on the e-bike systems by turning on the bike at the display usually, or if it has a separate app, you can manually turn on and off the BMS from there. And here we have a video covering multimeter testing, so the usual process that I go through when testing an e-bike battery. The first step is to get a reading from the discharge port. In this case, it's 51.6 volts, which is within the nominal range for a 13S lithium-ion pack. It does not matter if you have reverse polarity, it'll just show a negative voltage on the multimeter. Here's another example of two lithium-ion 10S battery packs. One of them is within nominal voltage, and the other one is below the low voltage cutoff threshold of 29 volts. For a pack this size. The BMS has done its job here and has disabled the charge circuit of the pack that is over discharged. As you can see here on this charger, a green and a red light mean there is no load, whereas two red lights mean the pack is charging normally and there is load, which is the case with the pack that has a nominal voltage. Now sometimes doing this is not the full story. The BMS discharge circuit could deactivate or close as soon as there is load applied to the battery, like in this instance here, where the capacity tester immediately ended the test because the voltage dropped below the low voltage cutoff threshold, due to the programmed 300 watts that the capacity tester attempted to draw from the battery, whereas the multimeter might not be enough load in itself to trigger this cutoff. If you don't have load testing equipment, simply plug it into the e-bike and look for any weird behavior, or if you apply any power on the e-bike where the battery might turn off abruptly. Lastly, if a pack is showing little to no voltage at the discharge port, it can be due to the fact that the BMS has disabled the discharge circuit. I'm simulating this manually here through an app with a smart BMS, and when I turn the discharge circuit on and off, have a look at what happens to the voltage in yellow on the capacity tester, which is acting as our stand-in multimeter. This may also be controlled by a physical switch, so don't forget to check for that, because that can also turn off the discharge circuit. In some instances, you may not see any voltage at all from the discharge port. This is more than likely that the battery has a blown fuse, which we'll get to in a second. To continue diagnosing via the multimeter, we want to get inside the pack so we can glean more information. The next thing we want to do is a continuity test on the fuses if the battery has any. If there is continuity, the fuses are intact. If there is not, one of the fuses may be blown and could need replacing. Now you may be wondering, what about the charge side? Well, usually on a lot of e-bikes, they have a barrel jack style charge connector, and if you try to stick two pins down there, it is very easy for them to touch and therefore cause a short circuit, as demonstrated by the continuity testing here on this multimeter. Where there is 4 zeros, that means there would be a big spark if the other end was connected to a battery. It is easy to slip and cause a short, so it is much easier to test the charge circuit from inside the battery where it's a bit safer to get the probes closer together, or simply test by just plugging in a charger that you know that works and seeing if it starts charging. The last two things to check with our multimeter are the pack balance and the overall pack voltage. If you're lucky, and in most cases with a careful hand, you can do this without extracting the battery core. Otherwise, you may need to remove the battery core to get access to these parts so you can test them. And by battery core, I just mean the internal parts of the battery inside the shell. Let's start with overall pack voltage. You're looking for battery positive and battery negative of the pack itself. This could be the same or similar to B positive and P negative, which includes the BMS. But if your BMS has a fault, it is likely very different. Or in some cases, it might not show any voltage at all or very little, meaning that the power has almost entirely drained out of the battery pack. Ideally, it should still be within a nominal range, but it could be hiding a cell group that is out of balance. So now we have to move on and check for pack balance. First of all, we want to find the JST balance connector. It looks like a long white plug. From here we can probe each pin to test the voltage of the various series groups. In this first example, this entire pack only has a variance of 0.02 volts, and that's not even at a full charge. Going back to my balance guidelines, I'd call this one pretty well within the realms of being balanced. This next example is of a pack where most of the cell groups are balanced, however there's usually one or two that are either completely dead or are quite different in their voltage. If deemed economical, it may be worth replacing one of these cell groups to resurrect this pack. More on that later on in this video. And our last balance example is where the voltages of each series group are all over the place and there's quite a large variance. This is almost always due to a BMS failure. While it's possible to replace the BMS and bring the cells back into balance, the damage may have already been done with some cell groups ending up working harder than others. Pack level fuse is usually on the charge or discharge side. Some packs have those fuses. It's more of an older tech and replaced by more modern BMSs, and it's designed to blow the fuse if the amperage is exceeded. So this is usually a protection for an external short circuit. First of all, I just want to draw your attention to this photo with the key. An interesting story behind this one. A customer decided to put the key into the charge port because the other side of the bike actually had the key barrel, and I think they must have got confused one day. But that caused a short circuit. You can see on the key where it arced across between the positive and negative terminals, and that actually resulted in a fuse blowing. So that fuse actually performed its function correctly and just needed replacing to repair the charge circuit for that battery. But now that we're back on the slide, let's cover pack connectors. For all things connectors and wiring, go back to the appropriate flowcharts that have been made for them. The common culprits you'll come across is usually excessive heat, so where something is burnt out, or if there's cycle fatigue, which is essentially the part being worn due to the plug being plugged in and removed many different times. Now, a quick addition to the video, I just wanted to cover capacity testing in the context of using it as a diagnostic tool. First of all, there are many different capacity testers that you can choose from. For the ones that I use, refer back to the tools video. Whilst a multimeter can determine a lot of the faults of a battery, sometimes you may come across a scenario where you need to actually test the capacity. It could be that the cells are all balanced still and the voltage is nominal, but there is reduced range. If you want to find out how much that range is being reduced by, testing the capacity of the battery is the best way to do it. The first thing that you need to do is create a protocol. For myself, I use a 300 watt continuous discharge, and for most e-bikes that are under 1000 watts, this seems to be adequate because it's a good balance of normal power usage. More advanced testers, you can create various protocols that have spikes in discharging. So you could have a program where it goes 300 watt and then suddenly jumps up to 1000 or back to 750 and all sorts. But the important thing is, once you've developed a protocol, it provides a reference. That reference is something that you want to compare all of your batteries that are using the same use case to. For instance, if you have all e-bikes that are under 1000 watts, you want them to use that same protocol so you can compare them to each other. An example of that is here, where we have 3 of the same batteries that have been repacked with pretty similar cells, and the test results were pretty similar in terms of the watt hours that were measured here in purple. Now, sometimes you can pick up anomalies through capacity testing. For instance, the photo on the bottom left-hand corner was of one of these packs, but it had a very badly imbalanced cell group. Therefore, it produced very little energy before the BMS cut off, resulting in only about 30 amp hours being measured, whereas the normal amount would be around about 430. And on individual cells, capacity testing is very useful if you are getting into repacking, for the purposes of measuring and ensuring that the cells that you use, whether they be new or second-hand, have enough capacity for the job. To summarize, when capacity testing is a diagnostic tool, low watt hours may indicate a pack imbalance, or there is wear or a reduced state of health on the battery pack or individual cells. Pack replacement. So this is something you want to consider. Depending upon your operation and setup, sometimes replacing with new, if you have access to it, is better. You want to consider your operational costs for the repacking versus the retail value of the pack. So is the opportunity cost if you have a technician or yourself that's spending time on repacking when that labor could be served better elsewhere to make profits in other part of the business? That's not a question I can answer for you because everyone is different, but consider that when replacing or repairing the battery, especially since it is one of the highest value components on an e-bike. Replacing a BMS. If you've already looked at the cell balance and that's okay and the pack voltage is okay, but you have a problem with a BMS where it's obviously burnt out or it's stuck in a closed state, then it is a good idea to replace the BMS itself. You want to replace it with a BMS that has the required voltage and amperage range. So voltage, look for the number of strings or series groups that the BMS can handle. For instance, this one here is up to 14S, and so it could easily handle 10S or 36 volt or 13S, which is 48 volt. You can get BMSs that go all the way up to 20S and beyond, which is 72 volt, but that's more of your high powered systems. And then amperage range, that's just what the MOSFETs or the switches between the C negative and the B negative can handle in terms of the discharge current and charge current, depending if it is a common or separate port BMS. For instance, this particular one here is rated continuous for 30 amps and can handle peaks of 90 amps. And ideally, you want to replace with a smart BMS so it has the capability to connect or communicate with other devices or apps, because having access to that information allows for a faster diagnosis if needed in the future. One final note, on a problem like this where the balance port is actually fused to the BMS and the resistor is burnt out, there could actually be drainage from one of the cell groups, so you definitely want to make sure the cell groups are actually still in balance. And here's a video of replacing a single cell group. Here we have a battery pack core where the BMS has gone into protection mode because one of the cell groups is dead. We use the multimeter to identify that cell group and then move on and check all of the other cell groups in this pack. All of the other cell groups are fine. And then we find our dead cell group by chasing the balance wires to find the positive and negative side of that group. Here are the 6 cells that need replacing. And we know that due to 2 reasons. First of all, the pack is a 10S6P, so there's 6 cells per parallel group. And second of all, you can see there's 6 cells connected together in the same orientation. So carefully, without causing a short circuit, we slowly dismantle the nickel strip from the cells, electrically disconnecting them from the rest of the pack. And using the multimeter, we can confirm that all of these cells are dead. We use the same model of cells as replacement and check that they are a similar voltage to each other and the rest of the pack, so the BMS can easily balance them with the rest of the pack. And if they are a similar voltage to each other, that means they're not going to discharge a lot of energy into each other when we connect them electrically in parallel. We attach the insulating gaskets to the positive end, and then we take the batteries and insert them into the pack in the same orientation as the ones that we removed. From there, we size and cut the nickel strips that we need to connect the batteries back to the pack. And then we use our spot welder to connect everything together. If you don't have a spot welder, simply use one of the other methods that we have described in an earlier video. For the nickel strips, it's usually good design practice to follow the parts that you dismantled earlier. As you can see, once I've done here, all of the connections are similar to how they were. Now that's done, we solder the balance lead wires back on, and then we begin reassembling the pack. Off camera, after I plugged back in the balance port, I made sure the BMS discharge and charge ports were back open and everything was functioning normally. And after all of that, I gave it a charge and put it on the capacity tester and got a good result. Remember, replacing individual cell groups isn't always bulletproof because the new cells usually have a different state of health compared to the old ones, and there's no telling when the next cell group might die. It's usually better to do entire repacks with the amount of labor that you're doing, but that calculation is up to you because every job is a little bit different. Now for a full pack rebuild, we've already covered the gist of that in the previous video when it came to pack assembly, but I just want to pull up a few reminders here and best practices to do. A more detailed, in-depth guide to pack building will be its own module, which I'll likely release in the future if there is a demand for it. But this slide here is useful to summarize a few principles. First of all, remember the different wiring that will be needed for your battery pack. All BMSs can be wired slightly differently. And the easiest method when it comes to how packs are assembled is you want to follow the existing pack wiring and take plenty of photos. For instance, this pack here, the cells are connected in a bit of a complex way. So what I did is I took a photo of how everything was assembled. I electrically tested and found all of the different cell balance groups. And in doing so, I made life easier for myself when I replicated the pack design when I did a full rebuild. In the meantime, if you need more pointers, go back and watch the video on pack assembly and safety. EV-Flow BC1 chargers. First of all, you want to check and see if you have the correct charger. If it's the incorrect charger, you want to replace it. We covered that earlier on how to select the correct voltage, charger, and the correct chemistry. Refer to the earlier video on chargers on how to select the correct charger. If that's not the issue, move on to charger wiring damage. For anything that is wiring or connector related, go to the W1 or W1B flowcharts. The next step is we plug in the charger and check if the LED lights up. If there's no light, first of all, we want to see if there's actually an LED built into the charger. If there is, that means we want to replace the charger, because if it's plugged in and there's no light, that usually means the charger unit itself is dead. Otherwise, if there's no LED built in, we want to move on to the next step, which is an output voltage anomaly. The way that we look for this is that we can use our multimeter at the terminals in a safe way to check the voltage output of the charger. For a lot of chargers, it will be pretty easy to identify the output. For instance, a 10S lithium-ion charger would show around about 42 volts, and a 13S or a 48 volt one would show about 54.6, plus minus a few fractions of a volt. However, you may come across some chargers that may not supply the full voltage right away unless they are plugged in. They may show a fluctuation between 1 and 5 volts or a very low voltage, but once plugged in, they will flick back to what a regular output would be for that charger. If you want to be sure, you can design a specialized cable assembly which the charger can then plug into, and then the other end plugs into the battery, where you can connect your multimeter in parallel to be able to test and see what's going on with the output once the charger is plugged in and charging the battery. If that's too tricky to do, one of the easier things to do is first of all just check and see if the charger charges over time, or get a replacement charger that's the same brand and model and see if it behaves differently from the one that you're testing. If you discover that everything operates normally with the replacement charger, that means the issue is with the old charger itself, so you want to replace that charger. If that's not the issue, move on to seeing if you have a loose connector. As illustrated before, sometimes the connectors that you have might not be a snug fit, and depending on how they are moved, they may or may not form a circuit, resulting in whether the pack charges or not. If you have a loose connector, you can replace the charger unit itself or just replace the connectors, depending upon what's more economical for you to do. Once you've done all these steps, check and see if you solved the problem. If you did, great. If not, repeat the BC1 because you could have multiple faults with the same charger, or check other EV-Flow charts because the offending component could be elsewhere on the bike. EV-Flow B1 battery. Step 1. Check the battery error codes. If your e-bike system has the capacity to do so, it will display error codes. If they are related to the battery, you want to use this list as guidance on how to fix them, or refer to the OEM user manuals for guidance. Next step, check for blown fuses. So this is as simple as just replacing a fuse. But if it's a repeated issue, you want to search and see if there's a cause that keeps on causing the fuse to blow. Remember, a fuse usually blows due to excessive current, so it could be a short circuit or an abnormal amount of load placed on the battery circuits. After that, check for wiring that is damaged or dirty. So again, go to the W1 or W1B for anything connector, wires, and cables related. And the next thing to check for is low range or low voltage. So low range, what we're referring to here is, does the battery have a reduced state of health? Has it been through many different cycles and it's not getting as much range as it used to? And the way that we find that out is by doing a capacity test. Sometimes that's just the reality and there's nothing wrong with the battery, it just has reduced cycle life. But that's different from the pack being out of balance, where there is definitely something wrong with at least one cell group. The initial step here is to repack or replace, and you do not want to recharge the pack if any cell group voltages are below the design specs. For instance, if you have a lithium ion cell that's not meant to go below 2.5 volts and you have a bank that is below that, do not recharge. Either replace the cells or the entire battery, which lines up perfectly with the steps that you do when a pack is out of balance. These can almost be combined together, but the reason why they're not is because natural cycle degradation is a thing. Just a quick one on checking for balance. You want to use your multimeter again on the balance plug to see if all of the cell groups are the same voltage. A pack that is more discharged is more likely to be out of balance than a pack that is fully charged, which is normal. And if you want to remember what is considered balanced or not, go back to the video where we covered that. After all of these steps, you want to finally check the BMS itself. You want to check and see if it's closed or if it's dead. If there's any indications of burning on the BMS, that's an obvious one. But otherwise, the charge or discharge circuits might just be fused shut for some reason with no obvious symptoms. You want to try reset the BMS or replace it. As shown earlier, a common way to check and see if the BMS is showing a closed circuit and it's not a smart BMS, so you can't see that on the app. You want to check the voltage of the B+ and the B- on the battery pack side of the BMS, where you are bypassing the BMS circuit, as compared to the B+ and P- circuits, which pass through the BMS MOSFETs. The BMS protections are in place, usually if there is a large voltage difference between the two. So once you've done all of these things, did it solve your problem? Great. Otherwise, repeat this process because batteries can have multiple issues. Check the other EV flow charts because the offending component could be elsewhere. Click here to watch the next video. It is the best free thing you can do to tell YouTube to support the channel. Otherwise, if you want to do more, check out the links in the description. Thanks for watching.